Nice to meet you all, everyone. Very excited to be hosting this webinar today. So let me get right into it. I can share my screen here. Okay, awesome. So quick highlight reel of everything that we'll be covering today. We'll be covering our new capabilities, multimodal data support capabilities in 51. So this includes our new MCAP support, which involves being able to visualize MCAP data directly in 51. So you can see all of your MCAP episodes within a single dataset in 51. This also includes our embeddings capabilities that helps you semantically search through your robotics or AV datasets and also interact with them in the feature space, looking at 3D embeddings. This will also include how we can index data from your containerized MCAP formats into a searchable and queryable and filterable sidebar in 51 that then enables you to quickly search across large scales of data. So yeah, that was a very quick highlight reel of everything we'll be going over today. So let's get right into it. So my name is Prerna. I am a machine learning engineer on the product team here at Voxel51. Today, obviously, the title of the talk that I'm giving and this webinar is debugging physical AI models using your multimodal data. And debugging physical AI models at its core means knowing how to work with your physical AI data. And physical AI data means wrestling with high cardinality, non-synced multi-sensor streams. And just by virtue of how these data sets are set up and how your data is set up, it makes it very hard to explore, align, and curate your data. Building robust physical AI models means having the tooling to be able to do these things, which is explore, align, and curate your multimodal data at scale. So a lot of what we'll be talking about today is how we addressed the challenges with working with physical AI data in our newest 51 capabilities. Okay, so like I mentioned, physical AI data is high cardinality, non-synced multi-sensor data. So this like 3D representation of it kind of drives home the complexity of this data. So you can see here we have kind of a 3D cuboid kind of thing where we have all episodes, which is every recording that you might have taken. And for one episode, you can see that there are multiple types of sensors and they're non-aligned and are each recording at different frame rates. So this just makes it such that you need to be able to store and work with data which has this structure. Now, why is that complex? High cardinality is just the start, right? Sync, exploration, aligning the data, curation of your data all depends on how you deal with the fact that it's high cardinality and the fact that it's unsynced. So by cardinality, I basically mean that there are a bunch of different sensors that are recording information within one single recording or one single episode. So take a robotics use case where you might have some industrial robotics example where you're manufacturing a part. You might have multiple cameras along with depth sensors that are recording information at any given time. And one recording where you're maybe assembling one part at one go or one iteration of the robot is basically going to include so much data. And this is multimodal because of the different sensors, as well as there's a time series component because each of those sensors are recording information over time. Along with that, something else that makes it really complicated is sync. The fact that all of these sensors have their own native frame rates and are recording at their own frequencies means that if you pause the clock at any given time, you won't find that all sensors have recordings at that time, right? There's going to be completely different alignments across these sensors. So what does this mean for exploring this data? You can't just scroll through it, right? Think of traditional computer vision where you have images. You could just scroll through all of those images to see what is going into your data sets. But exploring multimodal physical AI data and time series multimodal physical AI data means just scrolling through all of your recordings doesn't really give you a good idea of how your data set is set up. You would basically need the tools to be able to deep dive into every single recording and episode and play it across the time that it was recorded to understand what's happening. Now, once you've explored it, then comes the question of curation, which is how do you then extract interesting information from all of the recordings that you have over time? And how do you curate that data so you have high confidence that the quality of data you're feeding into your downstream models, which you're training to learn robot policies, are high quality and it includes all of the complex edge cases and includes all of the data you want it to include. So all of these four pillars, I guess, just make it really complicated to work with this kind of data. Okay. And now we talk about how we solved this complexity. So this is what we built in 51. The first new capability that's going to be included is native multimodal visualizers. So this is the ability to visualize your data in its native raw format. It doesn't assume any alignment of sensors. It doesn't assume anything about how the structure should be of your data, which is not multimodal native. This enables you to visualize multiple sensors simultaneously and play back all of those sensors at the same time. The second big thing that we've introduced is Columnar storefront indexing. Now, multimodal physical AI data is extremely complicated because of the cardinality and the lack of sync, but you also have a ton of data. So within just 5 recordings, if you've recorded for 5 minutes each, and 5 minutes each, and you have, let's say, 12 sensors, that's a ton of frames, right? You have 12 cross 5 cross 60 cross 5 again, which is 5 is the number of episodes, 5 minutes. So that's how many samples or frames you might have. And this is assuming you have these sensors recording at one frame per second. Now you have to also account for the frame rate of the sensor. So it's very high cardinality and it's a ton of data. It's just a lot of dense information that you need to be able to work with. And working with it means being able to search across that data, search across it reliably and search across it fast, because you need to find those specific cases where something interesting is happening. So Columnar Store, essentially what this does is we extract relevant information from your containerized raw MCAP format files and index them into analytical stores that enable you to do fast search and filtering. And then finally, the third thing that we're introducing is embeddings-based searches. Now, Columnar Store for indexing can only index metadata that already exists in your raw files. What about data that doesn't exist? So what about being able to find edge cases for which you don't already have labels, but you haven't already marked those labels in your datasets? How are you going to find those interesting edge cases and long tail events? So that's where embeddings-based searches comes in. So we embed all of your data, and it's not just embedding full episodes, because that takes away the fact that there's so much rich information over the full episode that's recorded. It's embedding small segments of time. So we have the ability to break down your big episodes into smaller segments, create embeddings for those smaller segments, and search across smaller segments when you do embeddings-based searches. So that includes semantic and similarity searches or visual similarity searches. So yeah, this is everything we'll be covering today, and this is how we tackled the problems in 51. I will answer all questions, by the way, at the end of the webinar. So please continue to post your questions in the Q&A widget that Jimmy mentioned earlier, and we'll get to them in the last 15 minutes of this call. Okay, awesome. So let's start looking at what we built. Enough of the slides. So I specifically mentioned visualization of native multimodal data. So here's kind of a quick tour of what that looks like. So the grid is a collection of various episodes that you want to visualize simultaneously. So let's say you are training a robot policy based on one data set that consists of a bunch of episodes. So this data set, which includes a bunch of episodes, creates one data set in 51. So every individual component tile here you see is one episode. And this is the 51 grid where you're able to visualize all of the different episodes that are in your dataset. So when you hover over one specific episode, you're able to visualize what's happening. And that's really valuable because you can quickly understand what's happening in a single episode. Beyond that, you can also change what stream you're looking at. So quick blurb about this dataset. This is the DROID dataset. But specifically, it's the point world DROID dataset, where on top of DROID, there were annotations that were added, which is basically depth annotations as well as point annotations that created new topics within the same dataset. So apart from the RGB cameras, there are essentially new sensors, which are depth sensors as well as what appears to be a LiDAR sensor, but it's just a point cloud that's annotated from the RGB images. So you can also change, like I said, what sensor you're looking at or what topic you're looking at. So I can, instead of visualizing the image RGB, I can visualize the point clouds here. Same thing applies here. I can hover over a single episode, it plays back that episode, and I can get a quick sense of what's happening in my data set. Now we'll go back to the image RGB. We'll open up a specific episode, and I'll give you a tour of our new multimodal viewer. So this visualizer, you can see, comes with a bunch of different tiles. The types of tiles that we support are image, 3D, map, logs, plot, message tiles. We also have the left and right sidebar, each of which has different functionalities. So in the left sidebar, you can see what the different topics you have are, and directly from here, you can jump into specific tiles. So let's say I want to visualize this points tile. I can just click the 3D button over here. It opens up a 3D panel for me, and I can visualize this points topic alongside all of the other topics that are present in this episode. And of course, within a points topic, you can toggle on and off with various capabilities. So I can toggle on and off my camera calibrations. So let's say I didn't want to see those, I can toggle those off. I can look at scene cuboids. So these were auto-labeled annotations that were added after the fact. So I can look at annotations this way as well. Let me very quickly show you this same multimodal visualizer on an AV dataset. So similar to DROID multimodal, I have this dataset called nuScenes multimodal. I'm going to open up one specific episode here. And we'll play back this episode. And here specifically in the 3D tile, you can see that we have map overlays that can be toggled on. We also have drivable area, we have lane markings, we have cuboids, and so on. So this really helps you deep dive into one specific episode and understand what's happening in that episode. Let me also very quickly show you what annotations and label tracks look like. So we can toggle on the matching annotations for cam front. And once you toggle those on, they basically show up as tracks at the bottom here. And this helps me understand where do specific objects occur in the scene according to the annotations that are present. And this becomes really valuable to get a quick sense for what is happening in my episode again. So based off of annotations, you're able to better understand where do certain objects appear within the timeline. So I can quickly go to that specific location and understand what's happening. One other really cool feature that I particularly love is our MCAP Explorer. So what this lets you do, okay, let me move this over here so it's full screen. And this MCAP Explorer lets me visualize any MCAPs that are present on my local device so that I can quickly use the same multimodal visualizer that we built for our 51 datasets, multimodal datasets, and I can apply them to a single local MCAP file as well. So here's just an example of a BitRobot recording from the BitRobot dataset. So this is from a kitchen organization. You can see this is quite long. It's about 3 minutes. Oh, I guess not that long. It's about 3 minutes and 22 seconds, but I can quickly scrub, see what's happening in various locations. So I can get a quick sense of what's happening in this data set. So this specific MCAP Explorer also becomes really valuable if you just want to do point visualizations of your data that's available on your local file system. Awesome. Okay, so that was just a quick tour of our grid and our sample model. What I want to talk about next is our temporal tagging capabilities. So sure, visualization is all well and good, but what is really powerful is being able to tag specific temporal segments of your data within an episode to say set aside that data for making sure it's added to your training set, or if you're doing some amount of debugging or something like that, if you want to mark that data to share with your colleagues, this is a very valuable feature for curation. So let's look at maybe this episode, and then we'll play it back. Okay, let's get rid of this. Cool. Standard, this robot is picking up this block. I guess it's going to drop it into the drawer and close it. So let's say I'm doing curation where I want to temporally tag all segments of time where this robot is performing a gripper close action. Now, of course, you can do that just with your sensor information, and that is something that I'll come to in just a second. But if you were manually annotating this data, how you could do that is with our temporal tagging. So here's where the gripper closed, or more accurately, let's say I'm specifically looking for cases where the gripper closed around an object. So not just when the gripper closed or opened, but when there was an object present within the gripper. So I can select that range of time and then annotate this as gripper closed. And what this provides me is a track, specifically this one, which I can see exactly where the temporal tagging occurred. And I can visualize that just that segment of time over and over. But where it becomes really valuable is when you do this at scale, right? You have multiple episodes within this one data set, and you temporally tag various different episodes with various different tag names. That's when it becomes extremely valuable. So I can toggle on this temporal tags overlay. And essentially what that shows me is where in this episode the specific tag occurred. So previously, before this webinar, what I did was I went and temporally tagged a bunch of episodes where the robot was dropping an object. So you can see this light orange is where it's being shown that within this episode, there is a temporal tag that's present that says that the object was dropped. I can select all of these dropping object examples, and it'll return all of the specific episodes that have that tag in them. I can, of course, hover over to see, okay, looks like dropping object did occur. Let's look at this one, which looks like a slightly different type of setup. We can play this, and it looks like here specifically is where the object dropping occurred, which, yep, looks right. So this temporal tagging becomes really valuable when you're doing curation at scale. So when you have multiple episodes within a data set, you're trying to understand or add some intelligence on top of your episodes within the data set for actions of interest that span a time range. That's when you would use temporal tagging specifically. Okay, awesome. The next thing that I wanted to talk about was embeddings-based search. Now, this is, I think, one of the most exciting features for me specifically, but also one of the most exciting features that we've heard a lot of our users say they are excited about and where they can find most value. Let's open up this embeddings panel, and I'll talk a little bit more about why specifically it's really exciting to me. So in this embeddings panel, basically what we did was we took every single episode, broke it out into chunks of, in the DROID dataset, we broke it into chunks of, if I remember correctly, 6 seconds. And in this nuScenes dataset, we broke every episode into chunks of, oh, it actually does say it here. So there's 4 seconds is what we broke it out into chunks of for the nuScenes dataset. And then we can look at the DROID dataset, 6 seconds. So this means that each point here in the embeddings view is features of those 6 seconds for a specific stream. So we computed this on 3 different streams: the point stream, which is the point cloud stream, and then 2 of the RGB streams, to understand what is happening within the episode without having to manually look through every single episode. Where this becomes really useful is if I want to understand if there are similar features that are shared across different episodes where the same action occurs or the same kind of movement or something interesting occurs, being able to mine that across your full data sets and doing that in this fashion becomes really powerful. So on this DROID dataset, you can see a bunch of clusters already forming, right? So let's look at a few points specifically in this cluster. So I can zoom in here, I can lasso a couple of points, and then it will filter down in the 51 grid to those, not only those episodes that contain those specific segments of time, but we'll also get overlays that show me exactly where that segment of time that matches is occurring. So here, let's look at this one. So you can see there are 2 matching tracks here within this episode for where this set of featured points occur in the embedding space. So what we can do is open this up. We look at this embeddings window matched, and then we'll press play. And basically, I think it's picking up specifically this nail polish bottle. And then, yep. So these 2 sections that matched both have the same type of action over the same type of object. And I didn't have to manually do anything to say, to add any additional intelligence or enrichment on this data, right? I just had to compute embeddings, and I was able to see that the exact same type of action over the exact same type of object is extracted over all of the episodes in my dataset. So again, here, this green track is the matching track, and you can see it's the same action, which is picking up the same type of object, which is a nail polish bottle, that occurs over all of the episodes returned. This also is very interesting because you can apply color by fields. So let's say I wanted to color by my operator. I can color by my operator and see if the operator, all of the episodes that they recorded cluster together in the embedding space. And this does happen. But on this episode specifically, that's not because the one operator performed the same type of task differently. It's more so because the operator was performing a completely different task. So that's why you see this type of clustering. But again, you can apply this kind of coloring over various other data that's also extracted from your MCAP. So signal data that I've extracted, like linear speed maybe. And that's something that I can do. It looks like for most cases, linear speed is pretty low, but it looks like there might be some cases where it's high. But it also looks like those cases where linear speed is high aren't in the feature space located far away from the cases where linear speed is low. So it might indicate maybe a little bit. It's a little bit of an outlier, but it's not so far out that you could say that these features find the variation in linear speed very well. So it is kind of blended in. These outliers are kind of blended into the larger massive embeddings points. So anyway, this is really useful to understand in the color by space also, to understand if outliers or clusters are happening because of a specific field. Now, similarly, in the AV dataset, it's also the same. You see a bunch of clusters. This was also a Quen model. So for both of these datasets, what we used was the Quen model. So this is a video embeddings model. So for each of the time segments that we previously specified, we encoded it with the Quen model. So we get a single embedding for each sensor for that segment of time. And that's what we're seeing. Each point corresponds to one sensor for one segment of time. What's really interesting also that I'd love to show is the ability to do similarity searches. So let's say I hover over a point here and then I want to find similar. I can basically do that directly from this embeddings plot. So it returns all similar episodes that contain similar segments for me. So I can see it looks like all of these were recorded in a similar kind of setting where it looks like it was this type of road, possibly even the same road that these were all recorded on. And you can also see where those matches occur. So here, ones where you can't see matches occur, it's basically the whole episode. But ones where you do see matches occur, it's a smaller segment of the full episode. Apart from just visual similarity search, you can also do text-based similarity search. So let's do something like pedestrian on a crosswalk. Okay. So this is not only finding episodes where a pedestrian was present on a crosswalk. Again, it's finding the specific segments of time where that pedestrian was on a crosswalk. So on this episode, it's right at the beginning. So you can see we'll pin this and then play back this section, and it's right at the beginning where this pedestrian is walking on the crosswalk. Similarly, there's a pedestrian right here on the crosswalk, pedestrian again on the crosswalk. So this is extremely valuable because, again, without enriching this data, without going through it manually and adding this intelligence on top of your data, you're able to find interesting cases semantically. Let's do another one. We can do something like red car. Okay. So it looks like we did indeed find the red car, but funnily, it looks like it's the same red car in a lot of these episodes. But that's possibly because in this nuScenes dataset, we took one long drive and broke it up into smaller 20-second chunks. But here you can see a different kind of red car as well. Okay. Yeah, let's see. Yeah, you can see it in the cam front slice and in the cam back slice. So one thing I'll note is even though the specific query you're looking for is present in only one slice, as long as that slice or stream of data, so for example here, it's cam front, as long as that stream of data is embedded, we know to search across all streams and to return results in whatever stream the matches occurred. So that becomes really powerful and useful for you to look across your data across all of your streams. So let's do the same type of semantic search in this DROID dataset also. Okay, we'll get rid of the color by, and let's do picking up an object. Okay. Okay. So it looks like there's a bunch of results returned, and it matches right at the end here. So since these were 6-second tracks, we would have to 6 seconds embeddings chunks. We would have to zoom back a little bit to see all 6 seconds. And it looks like it's picking up on the action of the robot more than the actual picking up of the object itself. But let's see. Let's see if we find some more interesting examples. Okay, it does a pretty good job on this specific episode where an attempt is made and a failed attempt is made and then a successful attempt is made. Awesome. So again, this semantic similarity search can be applied to all types of data sets to look through your data with text to find specific segments of time within each episode where there is something interesting occurring. And you can do that just with pure text search. Awesome. So just one final feature that I want to talk about is what I mentioned in the slides earlier, which is the columnar store for indexing. So, so far, we've mainly talked about visualizing your data and the embeddings-based searches. But one of the really, really critical pieces of a tool that can scale with your data as your data is scaling and as your processes get more matured, where you might automatically enrich your data with VLMs. So all of that metadata is what you want to search by. Columnar store and indexing your data becomes really critical. How we've solved this is one, MCAP is basically a containerized file format, which includes all of your sensor information within it. So to be able to search by that sensor information, you do need to be able to extract and index that data and then store it in external storage. So you're able to search, query, and filter by it really quickly. So in 51, what that means is we've introduced 4 new grains of querying. And those grains are basically events, labels, signals, and summaries. Some of them are self-explanatory, but labels, for example, is a self-explanatory grain, wherein if you have annotations within your MCAP file, you can extract those and search and filter by those. So, for example, I had cuboids that I generated using just a zero-shot vision model. And let's see, we have a bunch of labels here. So I can look through and find all episodes that have a specific label type. And yeah, let's choose something here. We'll do, I don't know, we'll do cardboard box, for example. So this was metadata that was previously present in my MCAP files themselves. And all I'm doing is indexing that and making it available for search and filtering. So you can see back here, there's a cardboard box, and that's probably why there was that label that existed in the first place on these episodes. Events are a way of defining derived events. So what that means is, let's say, let's take a case where the robotic arm is moving really quickly, and you want to tag all cases where that happens as a malfunctioning action of the robot because you don't want it to move that quickly. So you can create a derived event that is conditioned on a signal value. So let's say we have linear speed of the robotic arm. We can say when linear speed is between a certain start and end value, that's when I want to label it as malfunctioning. I can create those derived events, and they basically show up as events in the 51 sidebar. So one thing that we created an event for was gripper state change. So basically, okay, actually, let's get rid of the cuboid filter and just look at the gripper state change filter. So you can imagine almost every single episode has a gripper state change because every single episode involves looking at a robot performing a specific action with its gripper. But how those same gripper state change events show up is as tracks, again, at the bottom of your visualizer. So I can see here is where the gripper state changed, which makes sense. It went from open to close. And then here again, it went from close to open. So this kind of derived event is something that I could create and extract and index. Very quickly, also, we have this other grain called signals, which means you can extract whatever signal information is present. Let's say you don't want to lose signal information by giving it a name, right? That's essentially what the events grain does. If you want the raw signal information, I can extract all of the raw signal information and filter by that as well. So looks like I have a filter for when gripper state changes and when the linear speed is really high. So we can take a look. We have a couple of episodes here. Of course, it'll be hard to validate this, but we also have the plot title, which makes it easy for us to look at our linear speeds. So let's see, joint speed. Okay, so we could look at, oh, it's not joint speed, sorry. It is linear speed is what we want. Okay, so we can look at this linear speed. We can also look at it as a plot. And then you do see that there's a sudden spike here, but that's interesting. So this might actually be a bug, right? We don't see any change in the robotic arm's motion itself that would indicate high linear speed, but we do see a spike here. So this also helps give us information about where there might be noise in my data. So this signals grain, like I was mentioning, helps you extract information from your MCAP topics and index them, and then makes it searchable and filterable in the sidebar as well. Awesome. I think we basically went over all of the capabilities that I wanted to go over. These, to summarize, working with physical AI data is really hard. We've spoken to a lot of users building in this space, and we understand that the challenges in training good downstream physical AI models start with knowing how to work with your physical AI data in the first place. And because of those challenges, these are the three major pillars in which we've built our 51 multimodal capabilities. So I can pause here. Happy to take questions now.
I tried to do my best to answer the questions in real time, but I'm sure you can give a lot more color to some of the answers that I had to type out. The first one was a series of questions around some of the vernacular that we use or some of the terminology that we use. So it may not hurt to double click on what we mean about what we mean when we say multimodal data. What are these data types? And then the second
Yeah.
is what do we mean by native multimodal visualization? Maybe break that down. And if you can keep this all in your head, the last one would be what do we mean when we talk about episodes, streams, time tracks? How do those all kind of come together?
Yeah. Great set of questions. Good way to summarize the different terminologies that we've introduced as part of this webinar. So let me share my screen again really quick. So we have something to look at as I'm talking. Okay, awesome. So like I mentioned, with multimodal data, we basically mean data that has within it inherently multiple modalities. So any system that has multiple sensors that's recording of information through all of these sensors simultaneously is a multimodal recording, right? It's a multimodal data type, which has multiple sensors that have information recorded over time. So specific applications or industries where we see this, like I mentioned, are robotics and autonomous driving. Both of these industries have systems that have sensors like cameras, LiDAR, depth sensors, proprioception sensors, IMU, CAN bus sensors like that that are all recording information over time. And that's what makes it multimodal. So the other question that you asked was, what do we mean by native multimodal support? So if you noticed, in all of the capabilities that we mentioned today, there is nothing that makes you take data out of the native MCAP format, which is the raw recording that comes off of your systems, or the recording in which you store your data. We've seen that MCAP is really popular in both those cases. There is no step where you take this MCAP data and convert it into a format that's consumable by 51 because 51 can consume the raw MCAP data itself. So native multimodal support, kind of for a couple of reasons. One being that we visualize your data in the raw format it already is in. Right now, of course, MCAP is what we're supporting, but we definitely see that expanding to a lot more formats in the future. The second thing we mean when we say native multimodal support is in how we visualize the data. When you think about your multimodal time series data, there's the fact that it's multiple sensors simultaneously, but there's also the fact that there is a time component to it. So there is a logical way that you, as somebody who's working with this type of physical AI data, might want to visualize and store this data. We've already addressed the storage part of it because if you want to store it as MCAPs, great, 51 can consume MCAPs. But the visualization part of it is this is likely how you want to visualize it with multiple sensors that you can configure in a tiling system choose plots or maps that you want to visualize side by side alongside your visual sensors, and being able to play back all of those sensors simultaneously to understand the whole context of what is happening in a recording. So that's kind of why we say native multimodal sensor support. Um, I will also quickly go over what I meant by episodes, streams, signals, and then datasets. So one dataset in 51 is just a collection of recordings coming off of your system, so or device or robot or vehicle. This dataset, logically, you might want to create a dataset based off of all of the recordings from a specific time period, or logically, you might want to create a dataset based off of all of the recordings that will be fed into a downstream training pipeline. It's completely up to you, and that's why 51 is so flexible. You can create a collection of recordings, and each recording is what I am referring to as an episode. There are no limits on how long a recording or an episode can be. We're very flexible in 51, and we understand that depending on your use case and depending on what you're doing, you might need longer recordings, shorter recordings, so on. So there is no limit on how long an episode can be. But we've seen users have different desires on how long they want to make these episodes. So we've seen 20 seconds, we've seen 5 seconds even, but we've also seen 20 minutes and so on. So a single recording is just a chunk of time that you break down your recording into to interact with it. So that's a single episode. And that's completely up to you. There might be some logical reason you're doing that. Maybe from one full recording that's coming off of your system, you break it down into smaller chunks of 10 or 20 seconds where something interesting is happening, and you only work with that data and add that to your downstream training set. Then that is the data or episode that you would add to your 51 data set also. So hopefully that clears up some of the terminology.
Let's change gears here and talk about temporal tags. And the question was, are temporal tags generated on the fly, or are they manually created? So maybe you can talk about how temporal tags are created manually in the app, how they can be done via the SDK, but maybe it wouldn't hurt to touch on events, right, which are automatically generated in an indexing pipeline.
Yep. Yeah, great question. Temporal tags are one of the ways that you can curate your data manually. So on this data set, I don't have any temporal tags, but I'll show you on the DROID data set. So I did show you how you can add information or curation to your data sets by tagging a segment of time manually. So it's just shift click drag, and then we'll say test here. And then you can see that that basically shows up as a tag for you. But you can also do this in the SDK. And when you can do this in the SDK, that means that you don't need to do it manually, right? You can break down your episodes into smaller segments, have some vision language model run on it, and then add a temporal tag for you automatically. So that's definitely a very powerful use case that exists for temporal tags. But let's say you're not using a vision language model and applying that on segments of time. Instead, what you're doing is you want to mark off segments of time based off of some signals or streams present in your MCAP files. That's where the derived events occur. So gripper state change, for example, is just a name we've given to the condition where the gripper state goes from open to closed. So this kind of event is also something that can be done automated or purely through the SDK. So this is not something that needs to be done manually.
And let's take one more question or two more questions. The next one
Mhm.
is about vector DBs. So this question probably came up when you were showing the embeddings and the searching capabilities. Perhaps you can talk about how 51 is not a replacement for your vector DB, but instead it is a layer or an intelligence layer that you put on top of the vector DB, and maybe the sorts of vector DBs that maybe people are already familiar with that may integrate with 51 today.
Yeah, definitely. So, like Jimmy mentioned, Vector databases enable you to search through very large quantities of data sets using vector search, and they are designed and built to make that vector search really performant and really fast. Our ethos with 51 has always been that we don't want to be prescriptive about the exact set of tools you need to use in your stack, but we integrate with every single MLOps tool out there, basically. So if you have a vector DB of your choice that you want to bring in, you can absolutely use that vector database to store things like the segment embeddings that we were mentioning, and you can perform segment embeddings based searches on those. So um, very quickly sharing my screen here again. That's basically something like when you hover over a point here and do find similar. Right now, this is just using the built-in. It looks like my deployment might be down, but it's the same similarity search that I was showing you earlier. It returns samples in the grid which match the specific query that you have. And that kind of capability doesn't need to be tied to a specific vector database. You can bring in whichever vector database you would like.
And then our final question was around pricing, licensing, how it differs from the open source version. That will require quite a few links, so I'm putting those together in the response so people can index them. But we'll go ahead and maybe leave it there, unless probably our closing remark here could be, what does the future hold that you can share in regards to multimodal data? What can people expect in the coming year that you're able to share?
Yeah. Beyond this segment level embeddings, I think just doing this at a really large scale, supporting more and more data, and feeding into direct downstream training pipelines for vision language action models or perception models is where we're thinking about spending our time the rest of this year. So we understand that right now in the world of physical AI, data and iteration on data is where a lot of time is being spent. So we want to build the tools that let you do that quickly and reliably and powerfully, and also very importantly at scale. Yeah, continuing to build on this ability to do this at scale is where our resources are going for the rest of this year.
And I believe we can leave it there. That's all of the questions. I think the final question was a bit of an existential question, and we'll kind of let that one do what it needs to do. I've included in the Q&A the links to the enterprise feature breakdown, the pricing, the different ways that you can license 51 Enterprise, as well as a comparison grid that compares the feature sets between open source as well as enterprise. I included it in the QA. I'm also including it there in the chat, so you have it. Quick reminder, the presentation was recorded. We're going to gather up all of the links from the presentation, and we're going to gather those up and include them in the video description in the YouTube playback that we'll upload probably tomorrow, as well as look for an email in your inbox later tomorrow or on Thursday at the latest that will have all of the links. With that said, we're going to go ahead and leave the Zoom open for another 30 seconds or so. If you have any closing comments or questions, we can take it. So if you have feedback, do let us know, and hopefully we'll see you at an event soon. Thank you, Prerna, for the presentation.
Thank you so much.